Okay, good morning. The next chapter starts with a topic that's also very important in mathematics. It's set theory. Probably this is the most important theory in mathematics because everything is based on set theory, even numbers. So when you actually want to construct mathematics, you start from some axioms which you uh, agree on the truth of those axioms, and from there you start to construct everything, even numbers. So in principle, if you want to do it in the right way, you have to start learning about sets, and you don't when you are doing sets, you even don't know numbers, and then you start construct the numbers abstractly. So the notion of set theory is actually the very basic of mathematics. Everything in mathematics can be expressed in terms of set theory. And that is a little bit a hard subject, but not at this level. What we call it, sometimes they call it naive set theory or baby set theory. So even this is not the baby one, so it's a very small baby we want to study today. So you shouldn't be worried about the difficulties. So mainly it is philosophical difficulties going on. When you talk about set theory, you want to start from scratch. You don't have anything in your hand. You have to agree on something. And when there are some axioms you want to agree on them, then it is not clear that it will give rise to contradictions in the future. And actually it happened once in mathematics. So the father of set theory is George Cantor, or probably the pronunciation is Georg, I don't remember, but the family name is this. So he wanted to actually prove something about some other topics in mathematics, like Fourier analysis. The people wanted to find a relation between periodic functions and sine and cosine function. He was able to use the idea of set theory to prove some theorems there. Okay, and then based after that, some other people started actually extending the notion of integrals from what Newton discovered to a little bit more subtle sets, and everything was glorifying until actually a contradiction found by a mathematician and philosopher Bertrand Russell. But it was a very simple example. I might be able to discuss about that a little bit here for you. So he showed that, okay, we have been very uncareful, or we were not very careful about setting up this theory, because there are some internal inconsistencies in this theory. And it was very disturbing for the community of mathematicians at that time, because if that is not the case, it means that you can doubt about the work that they have done and proven a lot of interesting and discovered a lot of interesting mathematics there. So it was really disturbing for mathematicians. But fortunately, two other people, so mainly Ernst Zermelo, so finally were able to axiomatize set theory. They they presented some axioms, I think 9 axioms, that we accept them to be true, and everything else is constructed based on those axioms. And then they showed that if you are careful and use those axioms, then at least the inconsistency was presented by Bertrand Russell is now removed. So there is no problem there. But then, of course, Kurt Gödel, logician, a famous mathematician, showed that by proving incompleteness theorem, which is a sad story to mathematics probably, is that it doesn't matter how you axiomatize your topic, you cannot guarantee that there are no self-inconsistencies going on there. And that is a sad story in mathematics. So it means that might be there is some contradiction that next generations they realize, then we have to fix it somehow then. Or this is what we say that, okay, instead of being worried about that, we say that, okay, based on these axioms, these are the ideas that I can conclude from these axioms. Okay, so we cannot be certain that there are no self-inconsistencies anymore. So, but the point is that you might say that, okay, when we realize that inconsistency in the future, okay, we will add one sentence or one statement to our axioms. But that is the point. The point is that it doesn't matter how many axioms you accept and put it in your system, there is always the possibility that this will be a contradiction in the future. So this is why I'm saying that the topic of set theory is very close to philosophy somehow. So you realize that. Yes, please.
Do you have any example of the inconsistencies?
No, example of inconsistency, this is not part of the lesson, but it is not hard to understand it. I will talk a little bit, if possible, in this course to see what kind of inconsistency. I mean, let me start the set theory, then I will tell you what happens. Okay. So first, the main point is that the notion of set is not defined. It's a primitive notion. So you know that whenever you want to talk about a mathematical structure, you should have some words undefined. For example, you talk about geometry. So we work with points and lines and planes, but we don't really define them. Yes, so if I ask you what the point is, yes, so we work with points. We cannot define them rigorously. Yes, so for example, I don't know, how do you define a point? Because if I put this here, in your brain, it's a good representation of a point. I cannot draw this and say point A. Yes, you will start laughing at me because that's not a good representation. But this is not also a point because there are some dimensions to this point. Point is an abstract object living in your head because it should be zero dimensional. So this is not the case. Yes, so probably if I see it in a microscope, I can measure the length, I don't know, whatever. So that's not a one-dimensional object. So, but it's a good representative of a point. Yes, we discuss of points abstractly, but if I say that point A, you don't have any problems with that. Yes, you understand what I mean. But they don't live outside our imaginations. Is that clear? So that's an abstract notion when we talk about points. And that's the same thing for sets. How do you define a set? We cannot define it. For example, I can say this: a set is a collection of objects. But you understand, I'm just playing with words, English words, yes? Because then you might ask what the collection is. I would say, okay, a group of things. And you would say what the group is. Okay? So that's what I'm saying. You cannot define all the terms. Those terms that we have to agree on to have an idea about them is called primitive. They are called primitive notions of a theory. So the primitive notion of set theory is the set itself. Okay, so you have an idea of a collection, of a group of things. So this is enough for you to understand the set. But I want you to understand that you cannot really technically define that in the sense that I can define a prime number. You see, when you ask me what a prime number is, I can really define you if we have agreed of any terminology before that. I would say that a prime number is a number which is, first of all, a natural number. You understand? You see, I'm not referring to a prime number. I'm not using another word for prime number in my sentence. I'm saying a prime number is a natural number which is only divisible by itself and by 1. And all these terms have already been defined. Yes? So this is a good mathematical definition because in my sentence for defining a prime number, I am not referring to another word which is an English equivalent to the prime number. Yes? But this I cannot do with sets. Yes, please.
Yeah, I was just wondering, what would be the concrete definition of a number?
So there is no definition. So that's what I'm saying. Of course, we have some intuitions about numbers, but in mathematics, they wanted to do everything. So they wanted to do everything abstractly and rigorously. So they start from putting sets and axioms of set theory as the cornerstone and start building everything else on top of them. So if you ask me what is one, one is a set. I mean, it's a list or whatever you want to call it. So, I mean, this is the point. But of course, this is not historically the case. Set theory was started in the 19th century, yes, or probably a little bit earlier. But we knew about the concept of numbers, I don't know, thousands of years. Yes? Okay, so this is the first thing I want you to understand, that when I talk about a set, I am not going to define a set for you. But you have a rough idea what a set is. A set is a collection of objects, I don't know, a group of objects. Okay, that is a set. And what one thing is important, and you should make sure that you introduce your set in a way that any object in the world has two possibilities. Either that object is definitely in the set, or definitely it is not in the set. For example, I can say the set of one-digit prime numbers. This I consider a good description of a set. So this is legal in mathematics to say something like this. Because if I say 5 belongs to this set or not, what do you say? 5 belongs. There is no doubt about it. Yes? But if I say, for example, 4 belongs to this set or not, definitely not. Yes? But if I say the set of some natural numbers, or a few natural, the set of some of the set of some natural numbers. So I am not allowed to use this phrase in mathematics, because if you talk about, for example, 8, do you think this 8 belongs to this set? It's not clear, because the way that I have defined it is not clear. So you cannot make sure that 8 belongs to this one or not. So this kind of sentence that you see here, this is not acceptable when you want to talk about the word set. But when this is acceptable, yes, when you talk about the word set in mathematics, you introduce a set. One thing is mandatory. Everyone should be able, I mean, not being able to understand, to determine that. For example, if I say the set of all primes, do you think it's a good description or not? This is probably the way that I explained is not that correct. Do you think this is correct or not?
No.
Yes?
I think it's correct.
It's correct. So it might be my explanation or the English words that I use were not correct. The set of all primes is acceptable.
Why?
Because if you give me a number, that number is either a prime or not a prime, even though I might not have the knowledge at the moment to understand that. So is that clear? So if you give me a very, very long number and say that number is in this set or not, this is clear that it is either a prime number, which will be in the set, or it is not a prime number, which of course will not be in my set. Okay, even though, for example, I don't know, can I write a number? For example, let me say, I don't know, 1, 2, 3, 4, 5, 6, 7. This number, okay? This number is a prime or not. I don't know right now if this is a prime number or not, but this is clear. If I have time, enough time, and check it out, at the end, there are two possibilities only. Either this turns out to be a prime number, in that case it belongs to this set, or it turns out that this is a composite number, so it does not belong to the set. Yes? So this, I want you to understand that when I say that everything should be either in the set or not, it means in principle, you should be able to understand. There are only two possibilities for any object. That object is either in the set or not in the set. Is that clear? Not, it doesn't, it has nothing to do with your knowledge at the moment. In principle, every object, for example, if I say a triangle, do you think this object belongs to this set? For this case, immediately we say no, because this is just an object like this, and a prime number is a number, so it cannot belong to this. Okay, so this is acceptable again. Okay, so any questions? So you see, I haven't defined the notion of set, but you understand what type of sentences, what type of descriptions are allowed for talking about a set. Okay, so this is why, yeah, okay. So let me now tell you a little bit about the notations. Sets in mathematics are usually denoted by capital English alphabet, for example, A. So I can call this, for example, I would say, give it a name, A. And then we have this symbol that I have already used a lot when I was teaching you. So this means belongs to. And of course, this means does not belong to. Okay, so for example, here, if I say the set of all one-digit prime numbers, let me call it B, then I can say that 2 belongs to B is a true statement. Yes? Because this is the set of one-digit prime numbers. To be honest, I have to give you all, yes? The set, because I have to be very careful. The set of all one-digit prime numbers. So 2 belongs to B is a true statement because 2 is one digit, first of all. Secondly, it's a prime number. So T belongs to B is a true statement. But if I say 4 belongs to B is what? It's a false statement. On the other hand, if I say 4 does not belong to B, it's again a true statement. Okay, the punctuation rules about sets is that you have to use curly brackets. Okay, this is a have to, so you cannot just use other things you want to. You have to respect the punctuation rules. So, for example, here, if I want to write B explicitly, I would say B is equal to, I have to open a curly bracket, it's a have to, and then close it with another curly bracket, and then write the elements or members. These are the words we use. We say 2 is a member of B, or 2 is an element of B. And you need to list all the elements between these two curly brackets and separate them by comma. Okay? So the first one and the order does not matter. So 2, and then the next one is 3, the next one is 5, the next one is 7, the next one is finished, yes? These are the only ones, do you agree? 2, 3, 5, and 7. Yes, and then we close this. So this is the set of all one-digit prime numbers. But remember, order doesn't matter when you write a set. For example, if you choose to write B in this form, 3, 7, 2, 5, this is exactly acceptable. So the notion of order is not obligatory for a set. Okay, so now first of all, when two sets are equal, assume that A and B are two sets. We want to see when we call them equal. Okay? So they are called equal if they consist of exactly the same elements. Okay? Irrespective of the order of the elements. But of course there is something a little bit confusing here. For example, let me write A to be this set. Let me make them simple. By the way, the elements in a set doesn't need to be numbers. They can be just letters, words, anything you like. Of course, in mathematics, it's natural to talk about sets of numbers. Okay, but that is not a mandatory thing. So let me just write A as an English alphabet, little a, and let me write, for example, beta, a Greek letter, and let me write number 1. This is also a set. Yes, it's a collection of objects, an English alphabet letter, and a Greek one, and a number. And let me write B in this way. Beta, A, and 1. Are these two sets are equal? We say yes, because they consist exactly of the same elements. A, beta, beta, 1, 1. Okay, but the tricky part is that if I introduce another set, this I want you to know. For example, if I write beta, if I write 1, if I write A, and then if I write 1. Okay, these two sets are also equal. Okay, so you see 1 is repeating itself. So this is the way that you need to think. You pick an element from here. I want to understand that why A is equal to C. A is equal to C because every element in A is an element of C, and vice versa. Every element of C is an element of A. Okay, that is the point. Is that true? Yes. Let us check the elements of A. The first one is little a, which is an element of A. Is this also an element of C? Yes, it occurs here. Beta is an element of A. Is it also an element of C? So the answer is yes, and simply 1 is an element of A. It's also an element of C. So we realized every element of A is an element of C. But this is not enough. I have to check the other way around. Yes? Every element of C should also be an element of A. Is that right? Yes. Beta is an element of C. It's also an element of A. 1 is an element of C. This one, it's also an element of A. Little a is an element of C. It's also an element of A. Again, 1 is an element of C, which is also an element of. So these two sets, based on this definition, they have to be equal. And this is why you don't see this in mathematics, that an element is being repeated in a set. Because repeating an element in the set doesn't have any effect in the set itself. So it is better not to repeat things. So this is, by the way, implicit. When I talk about a set, I implicitly mean that no elements is being repeated. Because repeating the same element more than once doesn't have any effect in the set itself. So these two sets are called equal. Yes? But what about these two sets? For example, this is A and B, and then let me write B to be A, B, and C. Of course, it is clear for you that these two sets are not equal. But let us check again. Every element of A is an element of B. Is this true or false? Yes, because every element of A is also an element of B. So that is, for the time being, it's okay. But that is not enough. I told you, you have to check the other way around. Is it also true that every element of B is an element of A? This is not, because C is an element of B, which is not an element of A. So A and B are not equal. Yes? So repetition of an element, remember, will not produce a new set for you. For example, there is no difference between this. By the way, that is also sometimes good to know. If I ask you how many elements you see in this set, you have only 3 elements. One is 1. It doesn't matter which one you are talking about. and 1 is 2, and 1 is 3. Yes? But this is why this set is equal to 3, 2, and 1. If you see this equality, you shouldn't be surprised. Yes? This set and that set are exactly equal based on this definition. Why? Because every element of the set on the left hand side also is an element here, and vice versa. So that is why this set and that set are equal. Yes? Is that clear? Okay. So there are some terminologies that I want you to know. There is a set without any elements. Okay? There is a set without any elements, and we call this the empty set with this symbol. So that is called the empty set. Yes? So the empty set is denoted by this, or sometimes you open a curly brackets, there is nothing to put in, and then you just close it. So this is the empty set, yes.
Is that a Greek letter?
Yes, it should be a phi, because this is also epsilon. Yes. This is the same phi, but it has changed the form of it a little bit, so it is phi. In Greek, you usually write phi like this, or I don't know, you can see the way they type it. But I think this is a distortion of that Greek letter phi. Okay, so anyway, so the empty set is the set without any elements. Either you use this symbol for it or that one. Let me just talk, because I have seen some mistake. People say like this. Okay, this is not the empty set. If I want to give you a metaphor, the empty set is like an empty bag. Okay, but assume that you have a bag. Inside that bag, you have an empty bag. Okay, the first bag is not empty because it contains another bag, which that one is empty. So the bag of an empty bag is not empty itself. Is that understandable? That's the metaphor. So this is something like that you have a bag, inside the bag you have an empty bag. So it means that of course the original bag is not empty because it contains something in it. Okay, so be careful. This is not good symbol for denoting this. It doesn't mean this is not acceptable in mathematics. It is acceptable, but it is not the same as the empty set. It is a set containing the empty set. Yes? Is that clear? Okay, I will talk a little bit about these things before you, but for the time being, I want you to know the empty set. And in the other extreme case, I have the notion of the universal set. Okay, what is the universal set? The universal set so we denote it by capital U. It means the set containing all elements of the sets that I am discussing about them. So because I told you that there are no limitations for which things you can choose as elements. Yes? Yes? So I cannot give you, okay, so when I want to talk about a set, when I want to talk about sets, I told you that in principle I do not have any restrictions about what I can choose as elements. But then of course it is not that useful, because usually in mathematics we want to talk about set of numbers, or I don't know, set up geometrical shapes or something like that. So it is better when we want to discuss, agree about the universal set. The universal set is the set containing all elements of the sets that we are going to talk in that particular context. Okay? For example, I can choose the universal set to be R. Okay? In that case, this is not acceptable to talk about A to be A and B, if A and B are representing letters. Because When I say that I have the universal set R, it means that if I want to write a set, I have to respect to bring the elements from the universal set. So this is completely okay to write something like this. This is acceptable because the elements are all real numbers, and I told you that, for example, I chose the universal set to be R. But for example, if I clean this and say the universal set is N, this is no longer acceptable. Yes, because I expect the elements come from the natural numbers, but they are not. So that is the idea of the universal set. Usually, if I don't fix the universal set, you don't need to be worried about that. So it means that I am allowed to use whatever I want to. But if I choose explicitly the universal set, I have to respect that my elements are coming from that. Even if I don't say it explicitly, you need to understand that back of my head, I am imagining there is a universal set that I am choosing my elements from that set. Yes? So that's the notion of the universal set. For example, in the real extreme case, if I choose my universal set to be empty, so what happens then? There is only one set allowed to work with, and that is which set? Which set? If, of course, this is very boring, but I mean, if I choose my universal set to be the empty set, then there is only one set in this world, and that set is the empty set itself. So that's very, very boring. Yes? But for example, let me just make a little bit this idea understandable. Let me choose this one as my universal set. Of course, it might be, I don't know, even if you are a child, your universe is bigger than that. But anyway, assume that this is your actually universe. And then which sets are allowed to be used here? For example, can I write the empty set in this world? Yes, because there is nothing coming up. Okay. With another set, can I write this set? Yes. Which other sets I can write? I can also write this set. I can also work with the universal set itself. Is there any other set that I can work with in this universe? No. Yes. For example, let me choose this. If I give you the universal set to be A, B, and C, what are all possible sets that I can work with them in this universe? What is the first one is probably, again, you can write empty set. I can still work with the empty set. So you see that the empty set is always there. Okay, and then I can work with this set if I want to. I can work with this set if I want to. I can work with this set if I want to. Are there other sets that I can work with? Yes, for example, I can choose A and B. Should I write B and A again in my list? No, because by definition I told you that BA, the set consisting of B and A, is the same as set of consisting of A and B. So if I choose to work with, I don't need to write this again in my list. Okay, and then another one that I can work with is A and C. Another one that I can choose to work with is B and C. And then, of course, if I want to, I can also work with this. So that's the idea of the universal set. If you fix your universal set, it means that when you want to talk about sets, the elements of the sets should come from the universal set. I want you to understand, even if I don't talk about the universal set, it is always in my head that I am working in some imaginary universe. With some elements, I am choosing them. Okay? But sometimes I have to be explicit about the universal set. Another thing that I want you to know is the idea of a Venn diagram. Okay? Because usually these are abstract objects, and our brain apparently has evolved in a way that we can understand pictures better than numbers or abstract notions. So to solve this problem in set theory, to be able to draw some diagrams, this is the convention. If you want to draw something for the universal set, you draw it, this is convention, by a rectangle. And then if you want to represent sets, you draw them with other shapes within the universal set, usually like circle things, yes? For example, I can say this set, and I call it A. So it's a good representation, yes? You imagine that, okay, this is my universe, and I am working in that universe, so that is one acceptable set. But I am not allowed, for example, to draw a circle like this. Yes, because one part of it is inside, that's okay, but another part is outside the universe, which cannot happen. Okay, so this is what I want you to remember. You have to respect this. I can draw different, for example, sets. I can draw another set here. I don't know, I can draw another set here. They might overlap, they might be completely separated islands. We will talk about these terminologies later, but this is the picture that you should have in mind, okay? For example, in this situation, if I want to draw something, the universe consists of only 3 points. And then, for example, I can separate them and call it set A. And then this is the universe. For example, this set A is representing this set in this universe. Yes? Okay. Okay, but this I want to also introduce. So we learned what a set is somehow. We have a good understanding of what is a set. Even though we haven't defined that, we understood what is the meaning of sets being equal. But this is some terminology I want to introduce, and that is the notion of being a subset. Okay, and this is the symbol that I want to use. You write A, and then you use this symbol, and then you write B. You read it that A is a subset of B. This is how you read it. But what is the meaning when you say A is a subset of B? Probably it is clear for you. What does it mean? Of course, I have to define it. That is not something you can guess. But I think the word subset already hints you toward the right direction. Yes, please. So you need to make it a little bit more clear. Yes? So what do you mean? For example, you mean like this? For example, I write A and B. So assume that this is your set A. Okay, can you tell me a set B so that A is a subset of B is true? Might be I understand you better. A, B, C, D, yes, yes, that's correct. So A, by the way, if I say, does A belong to B, by the way, what is the answer? I will come back to these things later. So A belongs to B is correct or false?
False.
This one is false. Okay, we will talk a little bit about these things later. But this is true. A is a subset of B means whatever is an element of A is also an element of B. Okay, so that is important. So we say that A is a subset of B if for all x, if x belongs to A, then x belongs to B as well. So when you say A is a subset of B, in logical notations, this is the formula we write to describe A is a subset of B, but If you want to write it in words, might be that is easier for you to understand if you are not very familiar to read these logical formulas. You would say that we say the set A is a subset of a set B, and write, this is the symbol we use, if every element of A is an element of B. So this English sentence is a long one, but this is exactly summarized in this logical statement. This tells you that for all x, if x belongs to A, then x belongs to B. That's exactly that English sentence. So now, actually what you told me is correct. Do you agree that A is a subset of B? I have to check it in this way. You need to choose an element from A, all elements from A one by one, and check them if they are elements of B. If the answer is yes for all of them, for every one of them, then you can say A is a subset of B. Okay? So let us go and check the elements of A. There are two elements in A. I have to check all of them one by one. A belongs to A. It also belongs to B. So that's okay so far. And then I go to the next element, B. B is an element of A. I go inside B and see that, oh, this is also an element of B. That is enough. Every element of A is an element of B, so this statement is true. Okay, can you tell me what about this statement? Do you think that this is true? B is a subset of A. Is it true or false?
False.
This is false. If I say why it is false, what do you say? You would say, for example, C belongs to B, but does not belong to A. So this means this is false. Yes?
If A is equal to B, is A also a subset of B?
Yes, exactly. We'll come back to that. But not the other way around. Yes? So what you are saying is that if someone tells me that I have two equal sets, am I allowed to conclude that A is also a subset of B? This is true, yes. This is possible. If you tell me that A is equal to B, can I conclude the other way around? What do you think about this one?
Yes.
That's also true. But neither that one nor this one goes in that direction. Okay, if A is a subset of B, there is no guarantee that A and B are equal. Exactly like here. A is a subset of B is true, but A is equal to B is false. So that's extremely important to understand these things. Okay, so that is the notion of a subset. And what I did here, actually, I wrote all subsets. The tricky point is that is the empty set is a subset of another set or not?
Yes.
Okay, so what was saying? Okay, you want to find all subsets of a set. Before that, let me ask you some questions. Someone tells you that I have imagined a set. I don't give you the elements of the set. But something, of course, you know, the elements should have been chosen from a hypothetical or imaginary universal set. But forget about that, okay? Then I would say that, okay, I see this symbol. I see this statement. This is, by the way, a statement. The statement in mathematics is a declarative sentence which is either true or false. Okay? So I write A is a subset of A. I am declaring something which is either true or false. So I can call this a statement. So A is a subset of A. Is it true or false? You might say that, okay, you need to give me the elements of A so that I can answer this is true or false. Or you might say that no, I don't need to know the elements. I can still say something without knowing the elements. First one, which point of view you defend and why? Do you need the elements of A to know this is true or false?
No.
Oh, yes, you don't need to know that. Yes, but how can you defend that?
Well, if A is equal to B and is a subset of A to B.
No, I'm asking you, is this a statement true or false? You might ask me what A is. I am saying that A is a set. Which set I don't know. But then I'm asking you, is it true or false? If true, why? Yes, Casimir?
Every element of A is also an element
Of A. Because that is the only obligation. When you write A, so I told you that A is a subset of B means every element of A is an element of the B. So every element of the left-hand side set should be also an element of the right-hand set. If this is true, then this statement is true. Okay, now let us go back here. Choose an element from A, any element that you like. Is it true that that element is also in the right-hand side? Yes, because the right-hand side is still just the same thing. So this is important to know that every set is a subset of itself, no matter what. Okay? But the other problem is this. What about the empty set and this set? If I write this statement, is it true or false? Or do you need me first to give you the elements of A to be able to answer this? Yes?
It's false because no elements are there.
Okay, so that's one answer. So you say definitely is false. Yes?
I think we have to know the elements.
So we have to know the elements, two answers. Yes?
I think it's true.
It's true. Yeah, so which one is that?
So it's true.
It's true. This is a strange, might be, it's not, by the way, because when I give you the reason, you will definitely understand that. But this is a little bit counterintuitive in the beginning. Okay, so let me ask you something. When I write A to be 1, 2, and 3, and I write B 1 and 2, and then I write this statement that A is a subset of B. Is it true or false? This is false. But if I ask you why this is false, can you write a sentence for it? Since what?
Not all elements of A are present in B.
Okay, in other words, exactly, that's what you said is correct. In other words, there is an element. There is an element of which set? A. There is an element of A that is not
An element of B.
an element of B. So you see, you don't need a teacher to understand this. You could say that A is a subset of B is false because there is an element of A. If you want to emphasize what element is that, 3, that is not an element, an element of B. That's the meaning. So let us just say that A is a subset of B mathematically means what? Mathematically means for all x, if x is in the left-hand side, then x also is in the right-hand side. Yes? This is the meaning. Now, can you translate this mathematically? That's exactly what you said, but I want to write this. So how do you say that? A is not a subset of B means what? Exactly what you said. there is an element in A which is not an element of B. But if you write this like just using the symbols, what do you say? You say there exists. I don't know if I have already introduced that to you or not, but this means for all or for every. This means there exists. There exists an X such that, can you fill up this gap? Just read the sentence. There is an element of A that is not an element of B. How do you write that? Yes?
X does not belong to B.
Okay, does not belong to B is correct. But before that, there exists an X. Yes, X belongs to A and X does not belong to B. That's the meaning, yes? When you say A is not a subset of B, it means I was able to find an element in A which is not an element of B. That's the meaning. Okay, so I am claiming that the empty set is a subset of A. If you say no, this is not true, then it means that you agree that this is true, because they cannot simultaneously be true, yes? This tells you that the empty set is a subset of A. This tells you that the empty set is not a subset of A. So either this one is true or that one is true. I am claiming this one is true. If you don't agree with me, then you have to agree this is true. Is the logic clear or not? Because this is a little bit subtle. I want you to understand that. So this statement and this statement are called negations of each other in mathematics. So this tells you that the empty set is a subset of A. This tells you that the empty set is not a subset of A. Yes? Okay, either this one is true or that one is true. They cannot simultaneously be true or they cannot simultaneously be false. One of them has to be true and one of them has to be false. My claim is that this one is true. If you don't agree with me, there is only one possibility. Then you have to admit, you have to accept this one is true. Is that clear? The logic is clear. But what does this mean? The empty set is not a subset of this if you can succeed to find an element in the empty set which is not in the set A itself. But this is not possible because the empty set is empty. So this cannot be true. This is not true. So then this means that the negation of that is true. So do you understand? So this cannot happen. This cannot happen. So means exactly the same thing. A, here the empty set is playing the role of this A. This A is playing the role of this B. So let us write that. It means what? It means there exists an element X so that this X is in the empty set and X is not in the set A. Do you agree that this is the meaning of that sentence? But this is not correct because you are telling me you were able to find an element in the empty set. But the empty set is empty. You cannot find an element there. Yes, is that clear? This is the logic. So then you have to admit by logic only that the empty set is also a subset of every set. Every set. Is that clear, or do you want me to explain it? Because I know this is simple, but it's a little bit counterintuitive. Yes? Any questions? So let me make sure that you understand that. Okay, I am claiming that this is true. If you agree with me, okay, life is good, so we agree. If you say no, I do not agree with this one, then I hope that you see that you have to agree with its negation. Yes? If you say no, this is false, then you have to accept this is true. Logically, just by pure logic, yes? Okay, now let us explore the consequences of this statement to be true. When I say the empty set is not a subset of A, it means that I am able to find something here which is not there. But is it possible to find such an object? No, because the empty set is empty. It's just pure logic. Is that clear? Okay, so it's not that intuitive, but based on logic, you have to admit that the empty set is a subset of every other set. Yes? Is that clear? Okay. And then in Venn diagram, it's a good way to understand the notion of subset in a Venn diagram. Okay, so in a Venn diagram, we have this big rectangle for U. And for example, I want to represent this relationship between two sets A and B. For example, I draw this set, I say that this is set A. How do you expect me to draw B if I want to represent that A is a subset of B? Yes?
All of A is included.
Included. So this is a good representation. So I will draw this and I call it B. So this means that whatever is in A is already in B as well. Okay, so that's a good representation for this one. So it is good to see by pictures, you know. Whenever you want to see this, then you will have that. Okay, another thing about subsets is this one. Let me try to write all subsets. For example, if I tell you A to be the empty set, and I ask you to write all possible subsets of this. I mean, that might be a little bit extreme. Let me start from this one. I ask you to write all subsets of this set B. Okay, where do you start? I want you to list all possible subsets of this set. Yes? The empty set, because we just showed that. So that's not negotiable. This is, by the way, these kinds of arguments, they say that this is vacuously true. Or sometimes they say by default is true. Yes? Because if you say this is not true, then it means that the opposite should be true. It means that I should be able to find something here which is not there. I hope that you feel that this is a little bit new. So that's called vacuously true. Because the first assumption is false. Whenever the assumption is false, everything can be true, okay? So you start from here, but this is not the only one. Is there any other subset of B that you can imagine? That is the first rule. Every set is a subset of itself. Empty is also a subset of every set. So I started with the empty set, and then I also have to write the set itself. Is there something in between that I am missing in this case? No. How many subsets are there? 2. One of them is empty, one of them is 1. So these are the only subsets of the set B. Okay, if I write another set, we already talked about that when I was talking about the universal set. Okay, so what about this one? C, 1 and 2. What are the possible subsets of this one? Again, your list starts with the empty set and ends with, of course, the order doesn't matter, but let us be organized. I start with the smallest possible one, which is the empty, always. And in my list, what is the last one that appears? No? The whole C. Yes, so that will be the bigger one. But might be I have something to write in the middle as well. So of course there are. So this is one of them, and the other one is 2. So these are all subsets of this one. So for example, if you want, I can call them C number 1. I can call this C number 2. I can call this C number 3. It doesn't matter how you name them. C number 4. So these are all possible subsets of that set. Okay, let us go back to this a little bit non-trivial one. How many subsets I have here in my list? Of course, I should start again with the empty set and end with this set. But what this set is? The empty set. So that's the only one. So this is the only one. Here I have 1 subset. Here I have 2 subsets. There I have 3 subsets. Okay? And let me just write another one. For example, D, 1, 2, and 3. I want to write all possible subsets here. Again, the first one is the empty. The next one is, for example, this one. You have enough experience, so I write them a little bit faster this time. Yes? And then this is another one. Another one is this one. Another one is this one. Another one is this one. And finally, the whole expression, the whole set. And let me give them names here. So for example, I call this D1, I call this D2, I call this D3, and D4, and D5, and D6, and D7, and D8. Okay? One question that we will answer later, it's an interesting question. What is the question? Yes?
Maybe
How many subsets are there? That's a good question. I mean, this comes to your mind. That's the same thing happened for mathematicians. They try to answer that. Can you see the pattern? But the pattern might be clear for you, but later we will go and prove it when we reach to combinatorics, okay? But how many subsets do you think if I have a set with 4 elements? Here I had 0 elements, 1 element, 2 elements, 3 elements. Yes? 16. So the answer is 2 to the power of the number of elements. So how many elements are there? 0. 2 to power 0 is how much? 1. So there are 1 subset. There's 1 subset. And then the number of elements here is 1. So 2 to power 1 is 2. And then you got 2. And here you had 2 elements. 2 to power 2 is 4. And you really got 4 subsets. And here you have 3 elements. 2 to power 3 is 8. And you really have 8 elements. But you might say that this is a coincidence. I agree with you, but then we will prove that for you, that no, this is not a coincidence. And this led me to give you another terminology. So we would say that I want to talk about cardinality of a set. Simply speaking, it's a fancy name we say to the number of elements of a set. Okay, so the cardinality of the empty is 0 because there are no elements there. Cardinality of this set is 1 because the number of elements in the set is 1. The cardinality of this set is 2 because there are 2 elements in my set. Cardinality of D is 3. There are 3 elements of the set. And there is some symbol we use that's also a little bit unfortunate. It is the same as the sign of absolute value. But there is no matter of confusion. For example, here, if I want to ask about the cardinality of set C, I denote it by this symbol. But whenever I am putting C there, C is a set, it doesn't mean absolute value, of course. It means the cardinality, because absolute value is for a number, not for a set. So this is the cardinality of this set. When you see this symbol, I am referring to number 2. Why? Because there are 2 elements. When I say cardinality of D, I count the number of elements there, it becomes 3. Okay? So, this tells you that the number of subsets of a finite set, that is another word that I want to define. The number of elements, the number of subsets of a finite set is equal to 2 to the power of the cardinality of that set. So these are very fancy words, but I think it's very, very simple to understand it. But this we have to prove. We haven't proven that yet. Later we see why. Okay, but that was a rough guess, and that was good. Like it might be, it's a good exercise if we do this once for a set with 4 elements. It's a little bit boring task, but I think it's good. It's good to do it. For example, let me write E. This time, let me write it as A, B, C, and D. I want to write all possible subsets. According to that guess, how many of elements will be there? 2 to power 4. Because the cardinality of E is how much? 1, 2, 3, 4. So the cardinality of E is 4. So the number of subsets is equal to 2 to the power of the cardinality, which is 2 to the power of 4, which is 16. So we should be patient a little bit. We have to write 16 sets. But I mean, the order is not important. As far as you write all of them, that's okay. But if you don't want to be organized, then you will actually mess up. Okay? But so let it be organized. I start with sets, with subsets with 0 elements. 0 elements. So that's only one, and that is empty. Let me start with subsets containing only one single element. But that's also good to know these terminologies. Those sets are called singletons. Singleton. Singleton is a set with one single element. These are just terminologies. You don't need to know the names if you don't like to. Okay, so I want you to write all the singletons. How many singletons are there? How many? 4. So one of them is, of course, A. The other one is B. The other one is C. And the other one is D. Okay, how many subsets with cardinality 2 are there? We will answer all these questions when we reach to combinatorics. Either you have a rough guess about it, or you have to write all of them. Okay, so how should I do that? Of course, in this problem, I want to write all of them. So, I want to write all subsets with 2 elements. So let us be organized, because otherwise we will not be sure which one we have written, which one we have ignored. So I take A and I write it with B. I still take A, this time I write it with C. I take A, this time I write it with D. And I want you to understand there is no way to write B and A. You shouldn't write that, because BA and AB are the same sets. So, are there more? Of course, I don't need to use A this time. I use B. Okay, so I would say B and C. Again, I keep B the same, and I will choose D. Okay, is there anything else? 1, 2, 3, 4, 5. Is it enough, or we have one more? C and D. Yes, that's also. And then I hope that you agree with me. There are nothing more. So 1 of them, 4 of them, 6 of them. So far 11. So 5 of them are left. Of course, you know that what is down there in your list. What is that? The same set itself. A, B, C, and D. So in this row, I have to write all possible subsets which contain 3 elements. So what is that? A, B, C is probably, you see immediately, it's one of them. So I don't know how do you want to organize yourself. Let me keep A and B, but let us change C. There is only one element that I can switch to, and that is D. Okay, can you tell me another one?
BCD.
Can I write a still with A? I want to be a little bit organized. So A, C, and D. And now there is no hope that I can keep A, so let us give it up. And I start with B, as you said, B, C, and D. Do you think that there are something more there? No. And let us count. 1, 4 is 5, 6 is 11, 4 is 15, 1 is 16. So there are 16 subsets of that set. Okay? So about subsets, we learn two things. We learn that if I give you any set, it is definitely a subset of itself. You don't need to know the elements to answer this is true or false. We also learn that the empty set is a subset of every set. You don't know what the elements are. That was a little bit problematic. Hopefully you understand that. If you haven't, please read it or review the video again. If you have questions, come back to me again. There is also something about the universal set that I can write. A is a set, U is the universal set. What should I write here? This symbol or that symbol?
The second one.
The second one. Because according to the definition of the universal set, the elements of my set should come from the universal set by the definition. So this is the correct one. Again, you see, for none of them, I need to know the elements of A explicitly. Whatever A is, this is true, that is also true. Yes?
Is the universal set the set of imaginary numbers, or is it bigger than that?
No, that shouldn't be, by the way, that big. A universal set is a set that you define, and then after you define, you work in that set. So might be it is a big set or might not. For example, the set of real numbers is a default set, universal set when we want to talk about numbers. Might be you are interested in complex numbers, then you can say that, okay, now my universal set is the complex numbers. Or sometimes you just care about the integers. For example, in number theory, the universal set is usually the z, because the numbers involved are coming from the set of integers. Yes? Okay, there is one property I want to add to this list, and then you know about it actually. You see, the Venn diagram is a good way to imagine that. I give you three sets. Okay? And I guarantee you this is true. I also guarantee you this is true. You don't know about the elements, but that is my responsibility. I guarantee that these are true. What can you conclude about A and C based on your intuition? Can you say something, some relation is true between A and C? Do you want to say something?
Maybe you can say that A is a subset of C.
Yes, that's intuitively correct. From Venn diagram, it is very clear, isn't it? So if you want to understand this from Venn diagram point of view, so that is why it's an important tool in our hands. So this is the universal set. I want to represent this situation. So I would draw this A here. I have to draw B in this form because I want to respect this true statement. And I want to draw C, but I want to respect this true statement. How can I draw that? If I want to respect that B is a subset of C, I have to draw C something like this. But as soon as I draw C like this, A is also automatically covered by, is contained in this orange circle as well. So you see, by imagining Venn diagram, you can conclude that these three dots means that we can conclude that A is also a subset of B is true. Okay, so in other words, I want to add this in this list. I want to say that if A, B, and C are three sets, and you know A is a subset of B, and you know B is a subset of C, you can conclude, if you want to, that A is also a subset of C. But why this is true? This is good to imagine, but this is not a rigorous proof. How do you prove this statement mathematically? How do you prove that? You want to prove that A is a subset of C. How should you prove this? You need to confirm that whatever in A is in C. This is my goal. Okay, let me write this explicitly to show that A is a subset of C. Let X be and of course I write arbitrary, but you don't need to write it, it means arbitrary, an arbitrary element of A. We show that X belongs to C. First of all, read this sentence. Do you agree with what I have written? My goal, I know this is true, I know this is true, I want to prove this one is true. In order to prove this statement to be true, I have to convince myself that every element of A is an element of C. If I can confirm that, I am done. But I cannot work with any old elements, even I don't know how many elements are there. Okay? So I take X as a representative for an element in A. Which element? I don't care. This is why I call it arbitrary. So I would say let X be an arbitrary element of A. I show that X also belongs to C. Okay. Now what should I write here in the continuation? I would say that X belongs to A. Why? Because I myself assume that X is an arbitrary element of A. So this is my assumption. And there is another assumption that you gave to me, that is A is a subset of B. Okay, what can you conclude from these two statements? X belongs to A on the one hand, A is a subset of B on the other hand. If I want to, what can I conclude from this? Yes?
X also belongs to B.
So X belongs to B. Okay? So this is my assumption. This is the assumption given in the problem. If these two are true, then it's a logical argument by the definition of the subset that X also belongs to B. Now, on the other hand, you tell me that now I am allowed to use this as a true fact now, because that was the conclusion of this logical statement. X belongs to B, and I have another assumption in my hand, which is B is a subset of B, is a subset of C. So what can I conclude from the truth of these two statements now? X belongs to B on the one hand, B is a subset of C on the other hand. So what can I conclude about X and C? X is also a subset of, X also belongs to C. Yes? Okay, then I'm done. What was my goal? We showed that X belongs to C. I was able to show that X belongs to C. That's the end of the statement. I just want to show you that this is somehow not trivial. What do you think about this scenario? A belongs to B and B belongs to C. I haven't talked about these things. I will talk about them later. Can I conclude that A belongs to C? I just want to tell you that don't take these things for granted. You have to go and just understand it from logical point of view. A belongs to B, B belongs to C. A belongs to C. Is that right?
Yes.
So an example is that, for example, I belong to Sweden. Sweden belongs to the United Nations. I do not belong to the United Nations, yes? So notion of belonging and being subset are really different things. Okay? For example, if I write A, and if I write this, they are really different. This set contains one element. Its element is called A. This set is a set containing again one element. But the element of this set is not A, is curly brackets A, curly brackets closed. And they are not identical, they are not the same things. So, now let me just a little bit confuse you now, but I will fix it later. So which one of these symbols are true for these two? Is this one true for this situation, or that one is true, or neither, or both? I don't know. Yes?
I would say neither.
Neither. Any other ideas? Yes?
I'd say the first.
The first one. Yes, the first one is true, the second one is false. So this is true, this is false. Okay, think a little bit about this. I will start with this next time, okay? So I want you to understand there is really big difference between belonging symbol and being a subset, okay? First of all, I hope that you understand the difference. If you don't, I will explain this. So I will start from this idea next time. Any questions? Exactly, they mentioned that's a good example. I belong to Sweden. Sweden belongs to the United Nations. I do not belong to the United Nations. Yes. Otherwise, I would have get my salary from there. Probably is better, isn't it? Yes. Okay. Thank you very much.